A very good evening to all. So, welcome to the course that is Nanotechnology Science and Application, and I'm sharing my slides with you. Just let me know whether it is visible to you or not. So, my slides are visible to all. Am I audible? Okay, okay, fine. So, yeah, a very good evening to all. So, welcome to the course that is NOC25 mm44. So, the title of the course is Nanotechnology Science and Application, and this is your week 6 live session, and the course instructor is Professor Pratap Haridos, who is a professor in metallurgical and material engineering at IIT Madras, and I am your TA for this course. So myself is Suman Yadav, and I am PMR scholar at IIT Hyderabad. So yeah, so in this course, in this live session, we are going to discuss about what we have learned in week 6, what are the topics that we have covered. With the help of some questions, we try to solve those questions based on the whatever understanding that we made in week 6. Okay, so in week 6, we discuss about the impact of nanoscale on the optical properties. Okay, so nanoscale means when you go from macro scale to micro scale to nanoscale. Optical means whatever that color change, or like when you means with your eyes you can change, you can see the change in the material. Okay, that on the basis of that, when you go from macro scale to nanoscale, how this optical property is going to change. So here's one of the example that I have taken, and we also discussed in the previous live sessions also, like in first lecture itself we discuss about the color change in the materials. Okay, when you go from macro scale to nanoscale, what happens? Your material color changes. Here you can see this is the ag spheres and ag plates. Okay, so this is my ag means silver. Okay, so this ag is silver. So when you go from ag at macro scale, what we see is at macro scale we see it's like a silver color, right? Silver color. But when you go to the nanoscale, here you can see, so at nanoscale color changes. Here you can see, when not on the color changes, even if you go, when you are wearing the size also, when you are wearing the shapes of the material, the color change, you can see different colors. Here you can see in silver spheres, when you like at different wavelength, this is like a different what we say, these materials are different sizes as well as different shapes. So in spheres you can see that is this having yellowish color, and when you go this side it is like somewhat orangish color. Similar way, when you go from sphere size, sphere shape to the silver plates, the color is different. Okay, the color is somewhat like a bluish violet color, like that. So so this is the case when you go from macro scale to nanoscale. The part, so in this class we'll discuss why the color change we are seeing when you're going from macro to nanoscale, why there are different colors we are seeing, why we are seeing different colors, and at different sizes why the color is different. Okay, so in this live session we are discuss more about it with the help of some examples. Okay, so yeah, this is the first question for you, that the band gap of a material is 3.5 electron volt. Predict its color. Either it is red color, violet color, opaque or transparent. What is the correct answer? Okay, so your material is having the band gap of 3.5 electron volt. Predict its color. So what we learn in this week is that when we are having three type of systems. Okay, we are having metals, we are having insulators, and we are having intermediate of that, that is semiconductor. Okay, so in case of metals, we are having, this is the, okay, so in this case, wait. So in this case, what happens? We are having metals. So any system, any material when you take, it is having two bands. That is conduction band and we are having valence band. Okay, we are having valence band. Okay, so in case of metals, what happens that mostly the conduction band is my empty band. So it don't have anything like no electron, nothing is there. In valence band, it is completely occupied with electrons. Okay, so in metals, these two bands overlap. These two bands overlap. So here you can see this is my conduction band, and this is, I'll say, this is my valence band. Okay, so conduction band and valence band, they overlap with each other. That's where whenever so when we pass any frequency of light or any wavelength of light is falling on it, it shows the it absorbs the photons. Okay, this is my photons means whatever wavelength of light is coming and it is having energy of h mu, we call it as photons. Okay, so these photons will come and fall on the valence band, so it shows the transition, it shows that electronic transition, that is the electrons present here in this valence band, they show transition, they go from valence band to conduction band. Okay, because they are overlapping, there is no energy difference between them. Okay, so in this case, it is the electronic transitions are easy, whereas in case of insulator, this is my valence band, this is my conduction band. Okay, this is my valence band. So there is an energy gap. There is an energy gap between the valence band and conduction band. So all the systems, all the materials, their valence band is always occupied with the electrons. Okay, it is completely filled of electrons, whereas the conduction band, nothing is there. Okay, it is an empty band. Okay, so in insulator, there is a energy difference between my valence band and conduction band. Okay, and in semiconductors also, we are having the conduction band and we are having the valence band. Here we are having conduction band. In this system also, we are having that energy difference between the valence band and conduction band, but the energy gap compared to insulator, it is less. Okay, compared to insulator, it is very less. So even an external factor, when you apply an external factor, the electrons will jump from valence band to conduction band. Okay, so now we'll talk about the this gap we called is band gap. This gap we called is band gap. Okay, it is having some energy Eg. Here also Eg. Okay, so now if I want to transfer thus whatever the electrons present in the valence band, okay, now I want to transfer these electrons to the conduction band. How I am going to do it? By some external means. Okay, by some external means. So the external means is like that. When you incident the light, here I am telling this light. Okay, so light what we are having is, it is either IR wave, UV wave, or visible wave. Okay, so whenever so Okay, so whenever you incident the visible light, this visible light wavelength is 400 nanometer to 700 nanometer. Okay, so if I want to transfer the electrons from valence band to conduction band, so what happens? This is my Eg, and this Eg is equals to, so this is my what we say, photons. Okay, so if I want to transfer the electrons from valence to conduction band, so my photon energy should be greater than or equals to my band gap, whatever energy difference between the valence band and conduction band. So the photon is coming with that much of energy that is greater than this band gap. So the energy is more, the electron transfer from valence band to conduction band takes place. That's we call this electronic transition. So electronic transition happens from valence band to conduction band when the light falling on the system is having more energy compared to that of band gap. Okay, so if I incident the visible light at 400 nanometer to 700 nanometer, so the energy associated with the photon is, this is my light wavelength. Okay, this is visible light wavelength. Okay, and this is the energy related to photons. Okay, so this is the wavelength. In wavelength we say 400 to 900, but when you talk about in terms of photon, that is h mu. So in h mu what we do is we replace this mu with lambda, because we know the lambda value, right? So if we replace this, it will become h into c by lambda. Okay, so when you convert, this is my Planck's constant. If you put this value Planck's constant, if you put the value of speed of light, and when you put the wavelength number, okay, you get the energy. Okay, you get the energy in some joule, in joule term. When you convert it into electron volt, okay, because in semiconductors, in any electron transition, we talk about in electron band, whatever the band gap is there, we talk about in terms of electron volt, not in joules. Okay, joule will do, we talk when we are doing some work or like some heat release or like that. In that case we talk the energy in terms of joule, but when we comes to the material level, we talk about in electron volt. Okay, so when you convert this joule, because we got some value and this value is in joule, so when you convert this joule in electron volt, so the value associated with the photon having the wavelength 400 nanometer is in 3.1 electron volt, whereas in 700 nanometer it is 1.8 electron volt. Okay, because here wavelength more, E value will be less. Okay, so it is 1.8 electron volt, and 400, the photon having the energy of 3.1 electron volt. Okay, so if the okay, if I am having the energy of 3.1 electron volt, okay, if I am having the energy of 3.1 electron volt, and my Eg is around 2 electron volt or 2.5 electron volt, okay, or even 3 electron volt. So if the band gap is in 3 electron volt, in case of insulator 3 electron volt, so what will happen, the light will come, and because the energy of photon is greater than that of the band gap, so it will absorb the light and it will show the transition, electronic transition. Okay, it will show the electronic transition, and the electrons present here, it will excite to the conduction band, it will come here, and here it generates the hole. Okay, similar case we are having the in semiconductors also, but the band gap is low. So if we say it is around 1.5 electron volt or 2 electron volt or like that. Okay, so in this region, if I have to do if the band gap is in around 2 electron volt, the light will come and it will excite the electrons. Okay, so now in this case, the band gap of the material 3 electron volt. Now predict the color. What will be the color? So 3.5 electron volt, whatever the UV visible light we are having, okay, not UV visible, it is visible. UV is around 4 to 8 electron volt. Okay, 4 to electron, because the wavelength we are having UV, its wavelength is 100 to 400 nanometer. Okay, whereas in visible Visible region starts after 400 to 700 nanometer. Okay. So this is what uh, okay, so the wavelength of the light having this, if the light is falling and it is having the wavelength from 100 to 400 nanometer, it comes on the category of UV light. And when it is having the wavelength of 400, 700, it comes under visible light. Okay, so here in this case, it is 3.1 electron volt and it is having 1.8 electron volt. Similar way, when you calculate the energy of the photon in visible light, 100, it around 8 electron volt or like that, you will get the value. Okay, you just do the calculation, I'm not sure, but what I know is this is lies between 4 to 8 electron volt. Okay, we'll discuss more about, I think there's one more slide where we talk about this UV light. Okay, so when this light falls, okay, when this so now if I am having a band gap of 3.5 electron volt, what will be the color of my material? Okay, so when you talk about the visible region, when you talk about the visible light, it is only 3.1 electron volt. We cannot give more energy. So in that case, my material will be transparent. My material will be transparent. Why it is transparent? Because whatever wavelength of light is falling, if my material is having band gap of 3.5 electron volt, okay, so transition happens when my incident photon having more energy compared to the band gap, that keeps only my absorption of the light happens and the electronic transition takes place. Okay, when if my h mu, if my incident photons energy is less than the band gap, what will happen? Whatever the light falling on the system, it will transmit through it. So when the transmission of light happens, that means it will appear like a transparent. Okay, whatever material you are seeing, it is showing some color. That means some electron transition is taking place in that system. Okay, when there is no electron transition happens, that means my system is transparent. Okay, so my material is having 3.5 electron volt. If we talk about the visible light, it is only 3.1 electron volt. Maximum wavelength, that is minimum wavelength. The photon energy is 3.1 electron volt. That is the maximum limit for the visible light. Okay, so in that case, my band gap is greater than that of the h mu, that is 3.5 electron volt, and here only 3.1 electron volt. So in this case, there is no electron transition happens and the material appears to be transparent. So the correct answer is D. Okay, now we'll move to the another question. So this is my epoxy is a transparent polymer. Okay, and the epoxy composites with microfibers are reinforced are as reinforced are A. Opaque due to porosity, opaque due to the formation of interfaces between epoxy and the fiber. C is transparent and D is none of the above. Which one is the correct? Where epoxy is a polymer, so in the sixth week we talk about the Nephyon. So this is like a transparent polymer and we use this polymer to generate the nanoparticles which are stable and which is having less surface energy. Okay, so yeah, we'll discuss more about this Nafion. So similar to Nafion, we are having epoxy, which is a transparent polymer. Okay, when you mix this epoxy composite with microfibers, what happens? It either to become, because it's a transparent, either it becomes opaque due to porosity, it becomes opaque due to the formation of interfaces between epoxy and the fiber, or it will be transparent or none of the above. Which one is the correct? Anyone? Okay, so what happens, my epoxy is transparent. Okay, and when you add fiber, so this fiber is having different refractive index. Okay, this fiber is having different refractive index. So now when you mix this epoxy and the fibers, when you are mix epoxy plus fiber, so it is having different refractive index, it is having different. So when you pass the light, what will happen? The light will scatter. You know, scatter, what is scatter? If my system is that light is falling and it is transmitting, it is going back. So it's HMU is coming, HMU is going back. So it is like a transparent. This is my epoxy. Okay. Now if I add the fiber into it, it is having different refractive index. Yes, Santosh, you are correct, but the correct answer is B. Okay. Now you listen why it is B. Because now epoxy and the fiber, now it is like okay, so this fiber is having different refractive index and epoxy is different. So now what will happen? Instead of transparent, it will be scattered. Scatter means it will scattered in different directions. Okay, because the refractive index of fiber and epoxy are not equal. When it will absorb, when the refractive index will almost similar. Okay, that time the light will come and will absorb and transmit it. Okay, but in this case both the refractive index are different. So if we talk about the interface, the light will scatter. Okay, the light will scatter. So here you can see transparency requires a uniform medium with minimal refractive index variation, whereas the microfiber introduce heterogeneity in the system, and this heterogeneity scatters the center and opacity comes. Okay, so this opacity comes not because of the, it comes with the porosity, but mostly due to the formation of interface between epoxy and the fiber. Okay, porosity will, it will also come, but the opaqueness will come in the material because of the formation of interface between the epoxy and the fibers. Okay, so this is the correct answer, that is B. I think Santosh you got it. If you didn't, you just tell reply. Okay, because in this there is a mismatch of optical property between the epoxy is having different optical property, fiber is having different optical property, and there is a mismatch. Because of that, this opacity is coming because of interface of epoxy and the fiber. Okay, now the another question, that is silicon is used for solar cell application, that we all know that whatever the we are having solar cells in our home, so it is having silicon. So why we are using silicon in solar cells? Because it is having indirect band gap semiconductor, it is a direct band gap semiconductor, it is commercially available in large quantity, and D is it is high band gap. Which one is the correct? Anyone? So we'll talk one by one. What is the indirect band gap semiconductor and direct band gap semiconductor? Okay, and high band gap. If it is high band gap, we cannot use them. Okay, so this will directly neglect this because it is having high band gap. High band gap means whatever the visible light it is coming, it is not going to absorb completely. Okay, so that's why it will not going to absorb, and that's why it will it will not show any transition. So we cannot use this so silicon if you are using it, so that means it is its band gap for sure, its band gap is not higher. Okay, so now we'll talk about, it is an indirect band gap semiconductor. So indirect means, I think sir has taught. If you want we can discuss this because I'm going to take extra class, okay, on 17th. So that extra class will be like if you have any doubt in any of the topic, you just write to me, or you can just whatever that question answer that option is there, that there you can put, okay, this is not clear. So I'll try to discuss that one in the extra class. Okay, so this is the case. Okay, this is the case. This is my energy and this is my K value. Okay, so indirect band gap means when my this is my valence band. Okay, it is completely occupied. Whereas in this case, it will be like somewhat like this. Okay, this is not continuous. I think here also it will be like this. Okay, in this case also it will come like this. It will go like this. Okay, so in this case there is no there is indirect band gap. That means it will go here. It is only half. It is only half. Second half we have to go to that side. That means if I am having a system, it is having this kind of band gap. Okay, another one is having this will discuss. So these things will come in the spectroscopic topic, where we are having this electronic states. Okay, we are having different electronic states, and in different electronic state, so we are having different this kind of curves, and in that we are having valence vibration, what we say, energy levels. In that vibration energy level we are having rotational energy levels, and this is how it looks like. Okay, so this is my HOMO. This is what we call it, HOMO. That is my valence band. Okay, and this is my LUMO. This is my conduction band. Okay, so this is completely unoccupied. So, and this is the energy. This is the energy. Okay, so when the electron present here, that will go here. Either this is my direct band. Okay, this is my direct band gap, and it is like if it is having, it will move to this side. It will reach up to this. I think, yeah. In indirect band gap, what we are having, electron will excite to this up to this point, and then it will shift to the this side. Okay, this is my indirect band gap. Okay, so in this indirect band gap is like this, and direct band gap is like this. Okay, so silicon is like a the correct answer for that is, yeah, it is a direct band gap for sure. It is a direct band gap, but it is not like that. It is why we are using solar cell, because it is commercially available in a large quantity. Okay, so correct answer is this. It is a direct band gap, but the band gap is higher. Okay, and so the commercially if I using it for application, because of large quantity that is easily available in the market, and we are using it. Okay, it's a high amount, because whatever we are having the sand, that it contains the silicon. Okay, silicon oxide. Okay, that we generate the silicon from there. So yeah, this is the another case, but it is highly available. Its abundance is high. That's why we are using the silicon in solar cells. Okay, now the another question is, as the crystal size decreases, okay, as the crystal size decreases, more number of peaks appear in the X-ray diffraction. X-ray diffraction peaks shift to lower angle side. X-ray diffraction peaks broadens, or both B and C. Which one is the correct? When you decrease the particle size, when you decrease the particle size, what will actually happens? When you go from macro scale to nanoscale, what is the effect on the XRD patterns? Either the number of XRD patterns increase, okay, or the despacing will decrease, or the peaks become broader, or both B and C. That means both the peak shift will be there as well as broadening in the peak will appears. Which one is the correct? Okay, I think no one is replying. Okay. So here I'll explain is with the help of an example. So this is CDS. Okay, this is CDS and this is a woodsite crystal structure. Okay. Woodsite means what we know is we are having zinc blende and we are having woodsite structure. So this is the difference between zinc blende, phosphorite, okay, and this is woodsite. So difference is that this is HCP and zinc blende, it is having FCC. Okay, zinc blende, actually this is like related to zinc sulfur, zinc sulfide. So zinc sulfide, either it will be in a woodsite form or it will be zinc blende. Okay, so in this case both the what we say molecular formula is same. Okay, but if it's in zinc blende form, that will it will be in FCC's crystal structure. Okay, and when it is woodsite, that means it exists in HCP crystal lattice. Okay, so this CDS is in woodsite state. Woodsite state means it is having HCP crystal lattice. Okay, here you can see this is HCP crystal lattice. Okay, it is like AB. Okay, so in this case, erase this one. So in this case, here you can see it is having basically three different planes. Okay, 101, 100, and 002. Okay, so in 002, so one this is my 100 plane, that is at some theta of around what we say around 25 degrees Celsius, not degree, 25 degrees, and we are having 101 and we are having 002 plane. Okay, so these three planes are the important planes that crystal planes that CDS is existing. Okay, so in this case, this is the 1 micron. This is the XRD of CDS when its size is 1 micron. Okay, this is my CDS and size is 1 micron, and in that case we are getting the XRD peaks like this, very sharp and intense peaks. Okay, but when you decrease this particle size, to nanoscale, so here you can see this is the 1 micron. This is 1 micron, you are getting very intense and sharp peaks. Okay, when you decrease the 50 nanometer, 25 nanometer, 15, 10, 5, 2, 1. Okay, when you decrease this one particle size, here you can see peaks starts broadening. Okay, the peak starts broadening, but can you see any shift in the 2 theta value? No, because see here in 25 degree we are having 25, it is like around 27, we are having 27, we at 28 or 29, all the peaks are at the same 2 theta value. When you go from it is at same 2 theta value, there is no change in the angle. Okay, there is no change in the angle. What actually happening is, and you can see there is no increase in the XRD peaks. So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and the small will not count 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, here in this case 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, similarly XRD peaks remain same. Okay, XRD peaks, X-ray diffraction peaks remain same, and here there is no shift in the 2 theta value. So what actually happening is When you go from micron to nanometer, only the peak broadening is happening. Peak broadening, here you can see 50 nanometer is little bit broaden, 25 it a little bit more, and at 10, here you can see it will completely broaden. But when you go to 1 nanometer, 2 nanometer, even we cannot see in the XRD. So this is the zoom in view. So here you can see that 20 to 30, 20 to 30, there are three peaks. 20 to 30, they are peaks, but it will become too broadened that both the three peaks will combine together. It become a broad peak here. Okay. It becomes a broad peak here. So when you decrease the crystal size to nanoscale, from macro to nanoscale, what actually happens, that XRD diffraction peaks broadens. Okay, XRD diffraction peaks broaden, but there is no change in the number of peaks and the 2 theta value. Okay, 2 theta value will remain same, and its XRD peaks will remain same. The number of XRD peaks will remain same. Okay, now we'll move to the another question on the XRD itself. So this is like a problem. This is like a numerical. So you have to solve it and just let me the answer. So the particle size, the particle shows XRD peaks broadening at 2 theta 30 degrees Celsius. Not not it's 30 degree with full width half maxima of 0.6 degree using lambda. This is my lambda value, that is this is for copper K alpha. Okay, and this is some this is constant, that is 0.9. The crystallized size is approximately. Okay, so how you calculate the crystallite size? By using Scherrer equation. So in this Scherrer equation, what is that? Size is equal to K into lambda divided by beta cos theta. Okay, so what we are having? We are having K value, we are having lambda, we are having beta. Beta is nothing but this is lambda, that is wavelength of X-rays. Okay, beta is full width half maxima, and this is cos theta. Okay, this is like theta value where the peak appears. Or we have a crystal plane at which we are having crystal plane. At what angle the crystal planes are there. Okay, so now you have to calculate the crystallite size using this formula. Now you tell me the answer, because everything is given. K is given, lambda is given, beta is given, cos theta is given. What will the answer? I'll just write the values. It is 0.9 into lambda 0.154 nanometer. Okay, and this is 0.6 degree, and so this 2 theta, what we are having is cos theta. Okay, but given is 2 theta, so we'll divide this. 2 theta equals to 30 degree. So theta will be 30 degree divided by 2, so it will be 15 degree. Okay, so cos 15 degree. Now you tell me the answer. So in this case, here you can see what we need is nanometer. The size will be in nanometer. Okay, so that the size what we'll need is nanometer. If you use this formula, what you will get is nanometer degree inverse. Okay, we don't want this degree, so we have to convert this beta value in radian, theta of radian. Okay, so this radian, how it is? It will be 0.6 degree into pi by 180 degree. Okay, so now you solve it. It will be 0.9 into 0.154 nanometer divided by 0.6 into pi 3.14 divided by 180 cos. It will be cos is 15 degree. Now tell me the answer. So cos 15 is, this is 0.965 cos 15 and 0.6 into 3.14 divided by 180. It will be 0.00104. Okay. It is easy. 0.9 into 0.154 divided by 0.0104 into 0.965. It's nearby 14 nanometer. Okay. It is 14 nanometer. So it correct answer is 15 nanometer. Okay, it's nearby that. That is 15 nanometer. Okay. So I think it is everyone get it. So this is how we are going to calculate the crystallite size using the Scherer equation. Okay, so this is one more numerical related to that. That is the crystallite size of the material calculated by Scherer formula is. So size you have given. Okay, so size we can denote by S. Okay, it is 25 nanometer. And the full width house maxima is reduced by half. Keeping other parameter constant, the new crystallite size will be. Okay, so we can say this is S1 and we have to find out S2. What is given is, so if I have to apply this Scherer equation, so my size will be K lambda divided by beta cos theta. This is cos theta. Okay, this is beta. So this is constant, this is also constant, this is also constant. What is varying is size are varying and my full width house maxima is also varied. Okay, so now what is given is, what is my beta 2 is there, that is half of beta 1. That is what new, whatever the new crystallite is there, its beta value full width house maxima is reduced by half. Reduced by half means this is my beta 1, so it will become half. So if we apply this equation, if we say like S1 is inversely proportional to beta 1, right? Similar way S2 is proportional to beta 2. Okay, so we can write that S1 is equals to K lambda beta 1 into cos theta and S2 equals to K lambda beta 2 cos theta. Okay, when you divide, or like I want S2, so I'll keep S2 above, by S1 is equals to, it will become K lambda beta 2 cos theta divided by K lambda beta 1 cos theta. Okay, these things will cancel out. So it will become 1 by beta 2 and it will be 1 by beta 1. So this will go up. So it will be, wait. So it will be S2 by S1 is equals to beta 1 by beta 2. Okay, so we need S2. S1 is, so we'll keep the value that beta 1 is already there, and my beta 2 is half of beta 1, half of beta 1. Okay, so it will become 2 of 2. Okay, this will cancel out. So S2 by S1 is equals to 2. So S2 is equals to 2 into S1. So the S1 is 25 nanometer. 25 nanometer. So it will become, so S2 here, S2 will be 50 nanometer. Okay, it will little, okay. Yeah, that I'll correct it. Okay, when I'll upload, I'll make it clear. This is one. This is like this. This is different. Okay. So correct answer is 50 nanometer. Okay. Now we'll move to the another. So we'll discuss little bit more about this XRD. Okay. So this is what the XRD looks like. So we are having X-ray source on the left hand side. Right hand side we are having detector. And in the middle we are having my sample holder. Okay. This is my sample holder. Okay. So the system, the way it is rotate, because the detector and the X-ray source, it will rotate. Okay, so actually XRD of two type, that is theta theta type and theta 2 theta type. Okay, so if your detector and source, if your detector and source are moving, if your detector and source are moving and your sample is at constant, okay, it is constant, but your X-ray source and your detector is moving, that means it is a theta 2 theta. XRD is theta 2 theta. Okay, but what is actually your XRD source remains constant, your XRD source remains constant, that is here. Okay, and your sample and your detector will move, sample and detector will move, that will comes under the theta theta category. Okay, it is a theta theta XRD. Okay, so yeah, this is the difference. So what we are having is theta to theta. In theta to theta, what we sample will be at constant position. Your XRD source will move. Similarly, your detector will move. Either XRD will move upside. This will also move upside. It will go down. It will also go down. Okay, so that's what. So this is the angle. This is my sample. Okay, this is my sample. Your X-ray rays is coming. It is interacting with the material and it is going back to the detector. Okay, it is going back to the detector. So what is actually, it is making a theta. So it is coming by the angle of theta and it is reflecting at the angle theta. But it will be like, it will pass through this. So when you make it, it will become total 2 theta. Okay, it is 2 theta. 1 second. It will be 2 theta. Okay, so this whole thing we call it goniometer. This whole thing we call it goniometer. Okay, so different we are having different X-ray sources. Okay, so what we actually need is what you usually people use it, copper K alpha as an X-ray source. Okay, so how these X-rays are generated, you know that we are having nuclei, we are having orbitals. Okay, we are having orbital and we are having electrons in these orbitals. Okay, so whenever a light will come and it will remove one electron from this, so whenever this electron will remove, it generates one vacancy here. So to overcome this vacancy, what will happen, the electrons from the above energy, above an orbital, electrons and above orbital will come and will occupy this position. When they are occupying, they are generating then waves. This is what X-ray rays, we call it X-ray rays. It is removing some rays, that is we call it X-ray rays. Okay, so we are having different X-ray rays. So this is copper. So this system is whole copper. This is my copper system. So it is actually cheap. That's why we always make, mostly commonly people use copper K alpha, but we are having other sources as well. So like we are having copper K alpha that we commonly use, people commonly use. So its wavelength is 1.541 angstrom, that is most widely used. This in powder X-ray on thin films. Okay, we are also having molybdenum K alpha. Its wavelength is 0.710 angstrom. and it is higher penetration. It is higher penetration useful for single crystal XRD. So actually we are having two type of XRD. Okay, this is why theta and theta is different. Okay, we are having the kind of material you are having, on the basis of that we are having two different type of XRD. One is powder XRD, another one is my single crystal XRD. In powder XRD, actually in powder XRD we can have that powder, as well as we are, if you are having thin films, that you can check the crystal, means you can check the XRD and you can predict what kind of crystal structure it is having. Similar way, even a single crystal, okay, when you are having single crystal, that is, for that we are having another we are having another XRD that we will call is single crystal XRD. And this in single crystal XRD, the X-ray source what we use is molybdenum K alpha. Okay, so this molybdenum K alpha, its wavelength is 0.710 angstrom. Okay, it is having high penetration. It will go in depth. Okay, high penetration means we are having alpha, we are beta, we are gamma. Okay, so it will like the kind of like how much penetration it will show. Okay, according to that we are having different kind of sources. Okay, so molybdenum, it is it is having high penetration into the material. Okay, another one, it is cobalt K alpha. It is kind of toxic, and that's what and its abundance is also low, so people rarely use this one. That is copper K alpha. Its wavelength is 1.790 angstrom, and it is good for iron containing samples to avoid the fluorescence. Actually iron, when you use samples which is having iron, so for in that case what happens, that fluorescence kind of thing happens. Okay, so to avoid that, people use cobalt K alpha. Okay, for iron K alpha, its wavelength is 1.937 angstrom, and sometimes used in steel studies. Okay, so this iron K alpha, people use it, but for some particular studies. Okay, mostly commonly use it copper K alpha because it is easily available. Abundance is there, as well as it is cheap compared to other detectors. Okay, so yeah, these are the like different type of X-ray sources are there, and for different application people use them accordingly. Okay, powder XRD we use copper K alpha, single crystal we use molybdenum, and for iron containing samples we are having cobalt, and for iron we do the study of steel. Okay, now come to the another question, that is, which of the following statement is not true regarding template assisted synthesis? Okay, it enables the synthesis of particle with control size. B is stable particles can be synthesized. C is it can handle only small number of particles in large template samples. And D is life of the particle will be limited. Which one is the correct? So template assisted, we talk about the Nafion. Nafion, it is a transparent polymer. Okay, so we use this as a template. Okay, so which one is the correct? A, B, C, D. Which one is the correct regarding this template assisted synthesis? So first of all, why we are using this template assisted synthesis for nanoparticles? Okay, so whenever you make when you go from macro to nanoscale, okay, when you go from macro scale to nanoscale, okay, so this is how it's macro scale. But when you go to nanoscale, what happens? Its surface energy of particle increases. So when this surface energy increases, what happens? Your material's reactivity, your particles reactivity increases. Okay, your particles reactivity increases. Okay, so whenever, because it is having both of them is high surface energy, so both are reactive. So whenever they come nearby, when they come nearby, they show reaction and it will form a bigger particle. Okay, it will form a bigger particle, so its dimension will change. Okay, now I want a material, I want my nanomaterial that it will not react, it will not bind with each other. So for that system we use template assisted synthesis of nanoparticles. For template assisted we are having Nafion as a template, which is a polymer and it is transparent. So this polymer is tetrafluoro ethane. So it is polymer made from the monomer unit of this polymer. So the monomer unit of polymer, this Nafion polymer is tetrafluoroethane. Tetrafluoroethane, that means my having C double bond C and it is tetrafluoro. Okay, so whenever you want to make a polymer, what will happen, this double bond will break. So when you join two units, that is CF2 double bond CF2, this unit will go bind with that, it will go further. Okay, so it will become CFF and CFF. It will bind with the another unit, that CFF. Further it will bind with CFF, and that's how. So this is a dimer. Okay, and when you add it further, it will become a polymer. Okay, so this Nafion is somewhat looks like this: CF2, CF2. Okay, here CF, here CF2. This is further Y. One fluorine it is removed, it is connected with oxygen. So this is a side change. This is a backbone. Okay, this is side chain. So it is CF2, CF, CF3. Okay, and it is further connected to CF2, CF, oxygen, sorry, sulfur, double bond O, double bond O, OH. Okay, so this is one unit Z. So this is another. Okay, so this is my ionic part. Okay, this is my ionic part. Whenever you dissolve this proton will go away, H plus, and it will become O minus. Okay, so this is what it looks like. The Nafion looks like. It is kind of membrane, and it is transparent, and it is a polymer. Okay, so this polymer, when you make a like a big polymer, so what happens, this ionic parts will make a different monomers, backbone will be there, and you get some spaces. So it is like this is your polymer. Okay, so this is your backbone. So this area, so are different, they are having different polymer. So it is having SO3 minus. Further from, yeah, from here also it will come SO3 minus H plus. Okay, let me write it properly. This will be SO3 minus H plus. Similar way here also SO3 minus H plus. SO3 minus H plus. So different polymers, different polymer backbone will come this side, and it will. This is my. This is kind of hydrophilic. This is hydrophobic. This area is hydrophobic. But whatever this here, whatever this microcavity, we'll say microcavity. Okay, so whatever this microcavity we are having, so this is hydrophilic. Okay, so along with this proton we are having water. Here also we are having water. So now what happens? So when you do this template assisted synthesis, so which of the thing is not correct? So first is it enables the synthesis of nanoparticle with control size. Yes, for sure, this is correct. Okay, whatever, because when you make, I think we don't have space. Okay, Okay. So there are four steps that actually involved. First is when you are having this polymer, you first wash with nitric acid. Okay, nitric acid means you remove like whatever you are procuring this transparent polymer. Okay, and it is like a kind of sheet. It is kind of sheet, but this sheet is also like when it's coming, there's some something may deposit or some places some side reaction or some what we say tangling molecules are there, side chains are there. Okay, so that when you do with this nitric acid, when you wash with nitric acid, this whatever that extra things are there that will went off. Second thing is now whatever you are having this transparent polymer, you deposit in your salt, whatever the ion exchange you want to do, that particular salt you will take, like for example NaCl, I want to add Na positive. Okay, so I will, what I will do is I will make the solution that is having Na plus, and why I will disperse, I will like disperse or I'll put my transparent polymer there that I immersed in that solution. So what will happen, this proton, what is proton is there, it will this proton will be replaced by the sodium plus ion. Okay, the sodium plus ion will replace this proton plus. Okay, so the more time you will keep in that solution, the more number of sodium ions will come and more number of your H plus ions will go. So it will form like Na plus, NaCl or HCl. Okay. So HCl is a kind of stable as compared to NaCl. NaCl is kind of ionic. Okay. So now what happens? This Na plus will come and my HCl will be went off. Okay. As of that proton available here, it forms, it binds with Cl minus, it form a HCl. It will went off, and whatever the space is there, my sodium ion will come. Okay, so the more number of salt, number of metal ions I want to insert, more time I will immerse that template into the uh, that solution containing the salt. Okay, so if you want less number of sodium ions, it will form less number of sodium ions. The sodium ions will be there. Okay, now you have to pass the, now what you have to do is now you have to pass the H2S gas. Pass the H2S gas because it is Na plus. Okay, it is Na plus, it will kind of reactive. So when you pass the H2S gas, so it will form NaS. Okay, Na2S. Okay, this Na2S will there. It will like a stable. Okay, this will form my nanocrystals. So the more number of more time you will keep, the more number of that film you will get, and the less number less time you will keep your template into that solution. So you can less number of sodium ions will be there and less number of like small film will be formed. So it will control the synthesis. It will control it. So this synthesis will control the particle size. Okay, particle size of nanoparticle, whatever you are doing. If you want 1 to 100 nanometer of that thing, you will get 1 to 100 1 to 100 nanometer. If you want 1 to 50, you keep it for less time. If you want 1 to 10 nanometer, you keep it for little bit less time. So it is predicted that this template method is novel. When you are keeping your solution, if we talk about PBS, okay, if we talk about PBS solution that I think are taught, so in that in that thing, if you keep this template for 1 hour into this PBE2 plus salt solution, when you immerse your template your Nephron polymer into this solution for 1 hour, we'll get 1 to 10 nanometer of film. 1 to 10 nanometer. Okay, if you want, if you immerse for more time, if you immerse for more time for 10 like 20 22 hours, then it will be more than that. It will be like 1 to 20 or 50, that depends. So for 1 hour, if you immersing your Nephron into the salt solution, you will get 1 to 10 nanometer of your particle size. Okay, so it will form stable particles can be synthesized. Yes, true. It is like it will form stable because when they are far apart, first when they are close enough, they will show reaction and it will form a. Its a particle size is going to increase. Okay, when they are close. But when they are here in this micro cavity, they are stable. Okay, their reactivity is there, but they are not going to react with each other. So they are stable. Okay, and they are not means they are not going to combine. So yeah, this is the thing. So it can handle only small number of particles in large templates samples. It can handle only small number of particles in large template samples. So this is large template samples and it can handle only small number of particles. Yes, true. That's what we call it. It is a whatever nanoparticle you are getting in this method, it is like a dilute thing. Dilute. Dilute means you are having less number of nanoparticles in that template systems. Okay, the concentration is very very low. Okay, so yeah, this is the case, but the D life of particle will be limited. No, because yes, when they are nearby, their life will be limited. They show reactivity, they combine, or they can react with other things. Other if one nanoparticle of one material, nanoparticle of another material, they both combine. Okay, so their life will be limited, but in this case their life is not limited. So the incorrect answer is D. So this regarding the template assist synthesis, life of the particle will be limited. That is not true. Okay, now we'll move to the another question. Okay, I think I have to erase this one. Okay, yeah, I think it is visible. Okay, so which property of Nafion make it especially suitable as a host or template for metal nanoparticle synthesis? High optical transparency. B is perfluorinated hydrophobic backbone with hydrophilic ionic clusters. D is metallic conductivity and okay. C is metallic conductivity and D is high crystallinity. Crystallinity. Which one is the correct? Anyone? After 4, which is the correct for using this Nafion as a template or host for metal nanoparticle synthesis? So this A is true. Okay, this A is true. That is having high optical transparency. So this is my Nafion is transparent in nature. That is true. It is metallic conductivity. So that is not true. It is not a metallic conductor. Okay. It is high crystallinity. So this is having high crystallinity. No, these are polymers. Polymers are not crystalline in nature. Okay, when they are in solid form. Okay, when they are like what we say, when the order when the order of the atom is same. Like for example, if I am having carbon, carbon, carbon in a straight line, if this will go further, so it is highly crystalline. But if my system is not periodic in all direction, so if the periodicity is not there, that means it is not highly crystalline. It amorphous in nature. It is amorphous or less crystalline. We say less crystalline compared to that of like whatever crystalline material. If we are having, like for example, if I am having one atom, this is A, this side also A. So this is highly crystalline. Whereas if I take A, so in this case, this will be my highly crystalline. Okay, so this is not crystalline, less crystalline. Periodicity is not there. Okay, this is less crystalline. Similar case in Nafion also, I told you that the number of distribution of atoms is not constant. It is like varying. So that's why it is not highly crystalline. So correct answer is this. Yeah, high optical transparency is there. Okay, it is not high. It is only transparent. So the correct answer is B, that is perfluorinated hydrophobic backbone with hydrophilic ionic cluster. Okay, so this is whatever, this is hydrophilic ionic cluster, and whatever rest of the chain it was there. So this backbone is hydrophobic in nature. Okay, and this is perfluorinated. Perfluorinated, each carbon is having fluorine termination. So that is hydrophobic in nature. So the correct answer is B. Now come to the another question on the basis of TGA. So which of the following features can be seen in the TGA result of the heating of Nafion from room temperature to 400 degrees Celsius? First is removal of water, second is removal of carbon sulfur bond, third is breakdown of the side chain and backbone. Which one is the correct? All three are correct, only one is correct. C is 1 and 2 are correct, and D is only second is correct. Which one is the correct? When you having a nephron, when you are having nephron, okay, and you do TG analysis, thermogravimetric analysis. Okay, when you do thermogravimetric analysis of nephron, so actually there are three temperature ranges, that is 100 degree, or we'll say room temperature. We'll say room temperature to 300 degrees Celsius, 300 degrees Celsius to 400 degrees Celsius, and then 600 degrees Celsius. Okay, so actually there are three regions. Okay, so when you go from room temperature 300 degrees Celsius, we are having removal of water. Okay, 300 to 400, we are having removal of carbon sulfur bond. And then 600, okay, 400 to 600, what we are having is breakdown of side chain and backbone. Okay, so whatever backbone, that is fluorinated backbone, and the side chain, that is oxygen terminated, and then it is going. So that will takes place between 400 to 600. So in this question, what they are asking is heating of nephron from room temperature 400 degrees Celsius. What will happen when you go from room temperature to 400? There are three things is happening, that is removal of water and the removal of carbon sulfur bond. So both first and second are correct. So the correct answer is C, that removal of water takes place and removal of carbon sulfur bond takes place. Okay, why removal of water is happening at 300? Because when you go here, they little bit increase when you go to room temperature to 100 degrees Celsius. Okay, so boiling temperature boiling temperature of water is 100 degrees Celsius. Okay, but when you go at 100 degrees Celsius, whatever the surface terminated, okay, whatever that easily that bonded water is there, that is going to wait, that is going to remove. Okay, but when you go from 300, when you go from 100 to 300, there's some water entrapped in the cavities. Okay, that is bounded. Okay, so if my cavity is like this, okay, it is having SO3 minus H plus, here also SO3 minus H plus, here also SO3 minus H plus, and in between I am having water. So this is my oxygen, this is water, and this is water. So what actually happening is, so this H plus is there, it will bind with that, and it is forming HOHH. It is hydronium ion. Okay, so now there is a hydrogen bonding. There is hydrogen bonding, and also this is SO3 minus, and I'm having HOH. Somewhat interaction with the this one also takes place. So there is a hydrogen bonding between whatever water present in there. So it is hydrogen bonded to the whatever ionic part of this nephron is having. It shows it is the water present is there, it is form hydrogen bond with the ionic what we say ionic functional group. Okay, so this hydrogen bonding is little bit strong. So when you're going to heat, the temperature, when you're heating the nephron, so at 100 degrees Celsius, water available, that is CF2. So some water will be there on the surface of this, so that is going to evaporate. Okay, but for this water present here inside this cavity, micro cavity, for that we need more temperature, so that when you go from 100 degrees Celsius to 300 degrees Celsius, in at this temperature range, whatever present water present in this cavity, micro cavity, that is going to evaporate. Okay, and then 300 to 600 carbon sulfur bond, because this is kind of weak bond compared to carbon fluorine bond and carbon oxygen bond. It is weak bond because it is like it is having 3d orbital, it is having 2d orbital, no sir, 3d, and it is having 2p orbital. Okay, carbon is having 2p orbital, sulfur is 3d orbital, whereas in this case this is also 2p. Wait, this is also 2p orbital involved for the bonding. Here also 2p orbital, here also 2p orbital involved in the bonding. So this 2p orbital a little bit stronger compared to carbon sulfur, that is 2p and 3d orbital. So this will break first. So 300 to 400 degrees Celsius carbon sulfur bond will break, and then from when you go from 400 to 600, it is highly high temperature. So whatever that backbone is there, that is CF bond, it will break, or like carbon carbon, fluorine fluorine. So this will bond will also break, and the side chain will also going to break at the 400 to 600 degrees Celsius. Okay, so yeah, if someone asks when you're going from like 300 to 600, what phenomena happen, that 300 to 600 removal of carbon sulfur bond takes place and breakdown of side chain or backbone happens here. And beyond 600 degrees Celsius, temperature is greater than 600 degrees Celsius, in that case, because we are talking about iron sulfur, so this will be there. Okay, so this is the thing. Okay, now match the following. So this is my experiment and this is the output. So this is characterization techniques that we use to characterize the nanomaterials. Okay, so one side we are having XRD, TM, TGA, 4 pro measurement. So this XRD X-ray diffraction, TM transmission electron microscopy, TGA thermogrammetric analysis, and 4 pro measurement, that is for conductivity measurement. Okay, that I already told you. This is for conductive measurement. So the output of this is like stability. So whatever we are having this 4 different characterization technique. So this characterization technique is going to do what with the material. So when you do XRD, what will happen? Either it measures the stability, it measures the conductivity, it measures the particle size, it measures the corrosion resistance, and fifth is crystallite size. Okay, which one is the correct out of this 4? Which match is the perfect match? We are perfect, or which match is the correct match? Okay, so when you do the XRD, okay, when you do the XRD means it measures the crystallite site. Okay, it measures the crystallite site, that is A with 5. I think these two are there, so these two are going to eliminate. Okay, A and D are the option where XRD measure the crystallite site. Then we go to the B, that is TM. TM measure the particle size, because that is the atomic level. We are seeing that in TM we see the atomic level, how the atoms are arranged. Okay, to make a crystalline to make a like crystal plane. Okay, how they are arranged to check the crystal plane, and atom by atom you can view in TM. So it is a to measure the particle size. So here in this case B is 3, that is okay, fine. This is also like, we'll make like this, A, and this will go here. Okay, now we'll check C, that is TGA, that is thermogrammetric analysis. So this TGA thermogrammetric analysis, so we left with stability, conductivity, and corrosion resistance. Okay, so resistance anyway we are not going to measure. So TGA is to measure the stability, at what temperature how my material is stable, how it is going to decompose. Okay, going from room temperature to 100, 200, 300, 500. So material stability will take up to what temperature your material is stable. Okay, so TG will talk about the stability. So in this case, C is 1, C is 4th. So anyway, corrosion, it is not going to, resistance is not going to measure. So this is the correct answer. That is, the correct match is A. So this TGF is measure the stability, and 4 probe conductivity measure the conductivity. This is 4 probe measurement. It measure the conductivity. What we say is 4 probe conductivity. So we are having 4 different probes. So this is like sample. This is the sample. Okay. One side we measure the current. Okay. And another probe will measure the voltage. Okay. So actually they are different. There are 4 probes. So somewhat we represent is like this. So this is one probe, this is another probe, this is another probe, and this is another probe. This is A, B, C, D. So this A and D measure the current, and this B and C is measure the voltage. Okay, so from this you will get the conductivity of your material, and from conductivity you can measure the resistivity, that we know. Okay, that formula we know, conductivity and resistivity. So conductivity is inversely proportional to resistivity of the material. Okay, from if you get the conductivity value, you can measure the resistance value of the material as well. Okay, but for 4 probe measurements are for conductivity measurement only. Okay, and from there conductivity measurement you will get the data, and from that data you can determine the resistance. Okay, now come to the another question, that is, blue shift occurs when the particle size reduces, whether it is true or false. So when you reduce the particle size, okay, when you reduce the particle size, when you go from, again we always go from macro scale to nanoscale. So there's a blue shift. What is this blue shift actually? So this is blue shift related to the optical behavior of your material. Optical property that is associated with your material. Okay. So it deals with the optical. So blue shift is related to the optical property of your particle. Okay. So when are having a particle, optical means you are talk about the optical means like absorbance. Okay. We are having a system. Okay. So you are having a system. Okay, when you incident the light on it, when you incident the light on it, it is having photon h mu. So either it will transfer, it is transmit, or it will absorb. It will absorb. Okay. So there are two things happen, or scattering also happens. Scattering happens when you are having different phases or like that. So in that case, in this case, we are not talking about this. We are talking about whenever the light falls, either it will transmit or it will show absorbance. So absorbance means there is an electronic excitation happens. Okay, and when there is transmit means of uh, the wavelength of your light is smaller than the band gap, so it will get transmitted. Okay, so yeah, this is the thing. Okay. So when your material is reduce the particle size, okay, when your material particle size reduces, so this is kind of with having, this is my, if I say source, I'll make the set first. So this light is coming from some source. Light from source, and here it will be detected. Okay, it's from this detected light we input in the computer, and we got this is absorbance. A, I'm denoting this is absorbance. Okay, and this is my wavelength. So it will show some this kind of thing to show absorbance like this. Okay, it will show absorbance like this. Okay, so from computer, it will do some data, whatever the signal is coming, how much light is transmitted, and how much is get absorbed, and where it is get absorbed. So here you can see it is 100% transmitted, and there's an absorbance here. Okay, this is absorbance here. So at this particular wavelength, your material band gap is that much. Okay, so material will get absorbed, electron get excited. Okay, so this is what actually the scenario is, and from this signal whatever the transmitted light is coming, according to that it will do some calculation and it will come to the computer, and you see this kind of spectra, you see. Okay, so now what happens? Okay, so in this case what is actually happening is whenever the absorbance happen, we'll say we can determine the band gap from here. Obviously, how what is band gap? When you are your material is having, this is my conduction band, this is my valence band, or I'll say VB, and here is CB. This is conduction band. Okay, so now electrons are there. So whenever light is falling with some frequency h mu, okay, will falling with some frequency h mu. So this h mu, so I can say hc by lambda, hc by lambda. Okay, so it is coming like at very low frequency it is coming. Okay, so what we say is this is high wavelength, this is low wavelength. So why we always come from high wavelength to low wavelength? Because wavelength is inversely proportional to energy. So we always start from low energy and then we'll go high energy, high energy, high energy. So wavelength associated to that is going from high wavelength to low wavelength. Okay, so we always start when we are having neutral state. Now we are getting that light is coming, so it is coming from, so initially we give low energy and then we'll increase the energy, so the wavelength is going to decrease. Okay, so this is why we always move from high wavelength to the low wavelength. We always move from high wavelength to low wavelength. Okay, so now what is actually happening, the if my photon is having, it is having low energy compared to the this band gap, or we say threshold energy. Okay, we say threshold energy or this. So my light is falling h mu. So when the light is energy is low, wavelength is more. Okay, so it is started transmitting, it is transmitted, so we are having 100%. So absorbance is zero. We say absorbance is low, or we say zero absorbance is there. Okay. Absorbance is inversely proportional to transmittance. Okay. So absorbance is zero. That means transmittance is 100%. So whatever light is falling with this of energy, it is completely transmitted. Okay. So this is also h mu. Okay, so the energy is very low, okay, or the wavelength is very more, so it is coming and it is coming transmitting. Okay, as soon as the wavelength, or as soon as the energy, that is h mu, as soon as the h mu matches with the band gap, as soon as the h mu matches or equals to or greater than Eg, your material will absorb the light, and you see increase in the absorbance. That means at this point it starts increasing. That means this point is you can determine the band gap of your material. There are some other parameter also, that is also defined to get the exact value of the band gap, but we'll say at this point your value, your wavelength value is matching with your band gap. Okay, that's why the transmittance absorbance is happening, and that's why it is going. So it is always a like increase, sudden increase is there. So that is the absorbance. Now the wavelength, the energy is more, so more energy, like it matches with the Eg. Initial stages, like your h mu is less than, sorry, it h mu is less than Eg. This is the case when you're getting 100% zero absorbance, 0% absorbance, or 100% transmittance. Okay, another case is as soon as your h mu becomes equal to Eg. Okay, h mu becomes equal to Eg, like some transmittance happens, like around 20% absorbance and 80% transmittance happens. Okay, now the increase is increasing. Now h mu is going to increase. H mu is greater than Eg. Okay, you are giving more energy compared to the Eg, so your absorbance will increase to 60% and transmittance become 40%. And as soon as more energy you are giving, at one particular time absorbance become 100% or your transmittance become 0%. Okay, and from this values, from this transmittance and absorbance value, you will get this kind of plot. Okay, so here this what we say, your absorbance starts increasing. That means 20%. If I'm saying 20% means h mu is equals to Eg. So from this point you can calculate the band gap. Okay, so now the thing is, when you reduce the particle size, okay, this is what actually the scenario is. This is optical property of your material, nanoparticle. So now when you reduce the particle size, what happens? Your Eg value decreases. So your band gap will increase. Okay, the band gap will increase. So here, from here you will get the your band gap value. So while go from, this is A, this is B, and this is C. So the particle size, if we compare particle size, your C is the lowest, and then B, then A. A is having high particle size, large particle size, and C is having the low particle size. Okay, and the C is having high band gap. C is having high band gap, and it is having low band gap. Okay, high. So as I told you, this is high wavelength to low wavelength. When you're going from high wavelength to low wavelength, so UV visible wavelength is 400 nanometer to 700 nanometer. Okay, high wavelength means 700 nanometer. This is 700 nanometer. Okay, so when you're going from 700 nanometer to 400 nanometer, your wavelength is like going high to low. So the color associated with this, is red, and this is blue, or say violet. So the wavelength of light, okay, so wait. So the light having the wavelength of 400 nanometer, it appears to be violet in color. Violet in color. Okay. So you're going from red to the violet side, that is like bluish side. Okay. So this is a blue shift. So whenever the particle size reduces, your band gap increases, and your band gap means there is a blue shift occurs. So the correct answer is true. Yes, it is true that when you reduce the particle size, your band gap increases and it moves from red shift to the blue shift. Okay, so now another question is the primary reason for the blue shift in semiconductor nanoparticles, as particles wait let me as particle size reduce is either first is enhanced electron phonon coupling, B is quantum confinement of charge carriers, C is increased defect concentration, and D is surface oxidation. Which is correct? So in your material, there is a blue shift. In your semiconductor, there is a blue shift. Okay, so this blue shift is happening primarily because of when you're reducing the particle size. If you're going from, like, for example, if I am going from 50 nanometer to 10 nanometer, okay, this is like particle size I'm reducing. So there's a blue shift. There's a blue shift. So this blue shift actually happens because of enhanced electron phonon coupling, quantum confinement charge carriers, and increased defect concentration, surface oxidation. Anyway, this is not the case. Surface oxidation is not there is no role of surface oxidation. That increased defect concentration, that is also not a case. So the correct answer is quantum confinement of the charge carriers. When you decreasing 50 nanometer to 10 nanometer, one direction you are confining, you are reducing the size. So because of that, your blue shift happens. Okay, now moving to the another question. In quantum confinement, when the nanoparticle radius becomes smaller than the excitant Bohr radius. So out of four, which one is the correct? When you wait, okay. So quantum confinement happens when you are going from high particle size to the low particle size. Okay. So this nanoparticle radiation becomes smaller than the excitant Bohr radiation. So what will happen? The band gap decreases or band gap increases, band gap remain unchanged, or material becomes metallic. Which one is the correct? So for sure, material definitely not going to become a metallic. Okay, for metallic we are having this. What do we say? There should an overlap of. This is my conduction valence band, and this is my conduction band. Okay, this is my valence band. So there is an overlap of conduction band and valence band. This is the scenario where it becomes metal. Okay, if you are having this conduction band and you are having valence band, okay. So the Bohr radius means what are excitons? Excitons are nothing but when the light falls on your material. Okay, so the electron, for example, your electron is here. Your electron will go and excited to that whenever this h mu matches with the Eg, that is band gap. Okay, so in this case, the electron present here, it will go and excited to the conduction band. So now what actually happening is the electron which is going from valence band to the conduction band, it is generating a hole. So electron will go here and the hole will be there. So this is what we call is exciton. This is what we call is exciton. Okay, and likewise, why we are calling Bohr radius? It is somewhat similar to that of proton. Okay, it is somewhat similar to that proton. Proton is having H. This is H, and it will give the electron. It will give the electron. It becomes H plus. When it gives the electron, it becomes so the representation is different. So this is my H hydrogen atom, and you take off the electron. When you take off the electron, it becomes H plus. Okay, so this is similar to like that. So it gives the electron to the conduction band, it becomes hole is nothing but proton. So it is somewhat similar to that of proton. So that's what we in proton we are related with when we are having hydrogen, it is related to Bohr radius. It is having Bohr radius, that is similar to 2 angstrom, like this is Bohr radius. So this Bohr radius, it is so this exciton is similar to that of proton, so it is also having Bohr radius, that is exciton Bohr radius. So when a nanoparticle radius becomes smaller than the Bohr radius, okay, Bohr radius matlab means Bohr radius means whatever this 2 angstrom is there, if its value is going to decrease, what is actually happening is your band gap is increasing. Okay, your band gap is increasing, and that's why when because you are reducing the particle size, nanoparticle, if your radius is decreased means your value is decreasing. Okay, so in that case band gap is going to increase. Okay, so yeah, there's one more question. I think, yeah, these are the two last questions. So in journal, when light is incident on a material, When light is incident on a material, low energy photons get absorbed and high energy photons pass through. Is it true or false? Okay, so what actually happens is your material is there. Okay, this is your material. So when light falls on it, okay, this is what, when light incident on a material, this is my material, this is my sample if I say, and this light is falling on it. Okay, low energy photons get absorbed and high energy photons pass through it. Low energy photons get absorbed and high energy photons pass through it. So low energy means if we are having 0.5 electron volt, so it is like a 1 point, okay, light is falling on it and the photons having energy, so energy like 400 nanometer to 700 nanometer. Okay, so the energy associated with this is 3.1 electron volt and this is 1.8 electron volt. So what they are telling is, this is h mu. Okay, so they're telling low energy photons get absorbed and high energy photons pass through it. High energy photons, if my having a material, it is having the conduction band, it is having the valence band. So it is telling that low energy photon is going to excite, but high energy photons is going to transmit. That is not the case. Why? If your EZ is there, okay, if you are having h mu less than EZ, so there will be no there is no excitation happens. Only the whatever the light falling on it, it will pass through it. Okay, so it is h mu. So the passing frequency, passing light frequency is h mu. Okay, when your h mu equals to Eg or your h mu is greater than Eg, so when your incident photons energy is more than band gap or equals to band gap, then only that absorption happens. So this is false. This is false because low energy photons get absorbed. No, low energy photons is definitely going to transmit through it, and high energy photons is going to electronic transition going from valence band to conduction band. Because see, this is what now. This is the relation when you are having high energy photons greater than this. There only that absorption happens. So this statement is false. For example, this is my example. You are having glass. Glass is an insulator. Okay, right? Glass is insulator and is band gap. Sorry, band gap is electron volt. So this is my valence band. This is my conduction band. Okay, and the band gap is 8 electron volt. Okay, so if you're following that visible light, if you're following this visible light means you are having a 1.8 electron volt to 3.1 electron volt. So when it will fall, it will pass through it. Okay, it will pass. For example, if it's coming 3.1 electron volt, it is passed through the 3.1 electron volt. Okay, but when you incident that IR radiation, when you IR or sorry, when you incident UV light, when you incident the UV light is 4 to 8 electron volt. Okay, UV light is having 4 to 8 electron volt. So whenever this 8 electron volt is coming on this, then only that absorption happens. Okay, glass blocks UV. Okay, here it so if you are having visible light, it is photon energy is 1.8 3.1. So it is less than easy, not absorbed, glass looks transparent. But when you incident the UV light is having the photon energy of 4 to 8 electron volt. That is greater than or equals to our this band gap, and it get absorbed and glass block the UV light. Now your light will not transmit through it. Your light will not transmit through this glass, and it will block the UV light. Okay, so this is the case. So this statement is false. Now the XRD and TM can both be used to measure the particle size in polycrystalline samples. Okay, true or false? So this XRD and TM. So the XRD measure the polycrystalline crystallite size. Okay, this is measure the crystallite size. Whereas in this TM going to measure the particle size. Okay, TM measure the particle size, whereas XRD measures the crystallite size. Okay, so this is also false. Like both of them is not going to measure the particle size. TM going to measure the particle size because TM is like electron microscope. It is only shows like this is my plane, so it will show like this. Fringes will be there. So this fringes will tell that my atom to atom, this how they are arranged. Okay. So it will talk about this particles, how this particle, it will not talk about the plane, it will talk about the particle, it talk about the particle size. Whereas in XRD, XRD is a bulk property, is a bulk technique, is a not property, it's a bulk technique. Okay. So if you are having the sample, it will give the complete information, it will give the complete information of your sample. Complete information means what? How your planes, how many crystalline planes are there at what? 2 theta value. It talks about the crystalline planes. How many planes are there and what is the T spacing? Everything will be information will be given by XRD. That's why it talk about the crystalline size. Whereas it will talk about the particle, how the particles are arranged. It will not talk about that particles are aligned in this plane or it is at this distance at this 2 theta value. So it will talk about the only the how particles are arranged. So it will talk about the particle size only. Okay, so it is false. This TM and XRD is not going to they both cannot use they both cannot measure the particle size in polycrystalline samples. Okay, so in this case there is one more thing is like, if my light is there, if my so light is coming, or say radiation, so this radiation is having three parts, that is IR, UV and visible. Okay, so in this case UV visible will be taken by only 44% and this is taken by 3%. Okay, and the right 53% will be energy, sorry, okay, is of IR. So this is what, so 53% IR. So this is my so visible. So first is UV. UV is having 100 to 400 nanometer size, and 400 to 700 nanometer I'm having. So this is lambda value. So this is UV light, the light which are having the wavelength from 100 to 400 nanometer, that will say as a UV light. And the when the light is having 400 nanometer to 700 nanometer wavelength, we say visible. Okay, and when you are having more than that, when you are having more than that, okay, like 900, 1000 nanometer, that we say IR light. IR light. Okay, so whatever the radiation is coming, 53% is contribution of this, so we can write it like that: 100 wavelength lambda is greater than less than 400 nanometer. This is 3%. 400 to 700 nanometer, this is 44%. And lambda 700 nanometer to greater than that, that is 53%. This is IR light. Okay, so this is the overall thing. Okay, so I think, yeah, if you are having any doubt, if you are having any question, you just type if you are having anything. And plus I'm taking an extra class, so in that extra class, whatever concept you want to learn, or whatever extra thing that whatever not taught in this, or like just we introduce the concept and we didn't explain it properly, so that you can tell, the topic we'll discuss on the extra class that will be happening on 17th of September. Okay, so yeah, this is for today's class. Okay, I think you all understand whatever we discussed today. So we talk about the impact of nanoscale on the optical properties, going from macro to nanoscale. So this is like This we started in the first class, right? We started in the first class where I told you that we are having gold and silver nanoparticle. When you are having bulk, it is somewhat like a golden color, okay. But when you reduce the particle size, when you reduce the particle size going from like 10 nanometer, 100 nanometer, the color is changing, as well as along with that even the size is changing. If the nanometer scale is same, like for example 15 nanometer, 50 nanometer, but one is like sphere, another is like a prismatic, so their color is also different. So this is the what case is how the color is different for silver. When you are having sphere, age is sphere, when you are having same wavelength like 300 to 1000 nanometer, you are having the wavelength, and you are having gold sphere, like silver, silver in its spherical form. So it absorbs the wavelength here, that is so this is like red, right? High wavelength is red, low wavelength is violet. Okay, low wavelength is violet. Okay, now you tell me why we are going from high wavelength, we are having red color. But in this case, the absorbance is happening at low wavelength. Okay, the absorbance is taking place at low wavelength, but what we are seeing is yellow, orange, this green color. But in the high wavelength, the color is red. It should show like a violet color or blue or greenish shade. But why it is showing that yellow orange color? Because whatever that light incident we see the complementary color. Okay, so there we are having Vibgyor, right? It is like 5, I think. Okay, so I think Vib uh, OR. So it will be wait. Okay, so whenever your wavelength is violet, that is blue color. Okay, so or like violet for around 400 or like that, we are having violet or blue color. So blue color will give the violet color. So the wavelength, your material is absorbing blue color, but it will show when you see it is show orange color. Okay, so your material is there, and your it is absorbed the frequency of 400 nanometer. So 400 nanometer corresponds to violet region. It will show violet color. It absorbs the violet color, but you will see the yellow color. You will see the yellow color. Okay, we always say the complementary color. So when light absorbs violet, when light absorbs blue color, you will see orange color. Okay, when it absorbs green color, you will see the red color. So here you can see at 900 or say 700. Okay, in 700 we are having red color. Okay, we are having red color, but what you will see is green color. So here you can see the green or like a blue or violet color. So yeah, when they are absorbing at high wavelength means you will see the complementary color, that is having low wavelength. Okay, so yeah, this is the case. That's why here in case you can see the wavelength observing at low wavelength, but we are seeing the different high wavelength colors. Okay, so light absorbs whatever color is absorbing, its corresponding color, complementary color you will see in your material. So yeah, this is the case. Okay, we'll discuss more about in the next uh, live session. So till now, thank you. Now you all can leave this